Now let's take a look at another feature of C that C++ changes dramatically. And this is almost a preview of something that's going to show up again in a couple of weeks. We have to see it now just to get used to the idea, to see the notation used in this language. But it turns out we're going to spend an entire third of the course later on extensions of this concept. And it actually also turns out that the original motivation for C++ being invented is in fact related to this, to what we're going to discuss in this video. But much of this video is actually going to be a preview of some material that's going to begin in a couple of weeks. Recall in C that we're able to create our own structured data types. We're able to create our own types that correspond to containers of data. And we call these things, so the general term we use in C is a struct. So in this context, the type point is an example of a structure type. However, in C, you might recall, there are two different ways of defining structured data types, and C++ keeps basically neither of them. You might recall in C that one of the ways of defining a structure type is to write something like struct point, and when you're done, when you've defined the type that way, you end up with a type whose name is struct point. And yet in this program, I seem to be able to use the word point, I seem to be able to paste things in by accident, and then use the word point directly as the name of the type. You'll also recall that in C, the other way of writing a C structure type involves the word typedef, and we're not using that here either. And that's because when C++ was developed, the whole way that structured data types are created had to be overhauled for reasons that are going to become clear pretty quickly in this course. So it turns out in C++, if you want to define a structured data type, you always define it this way. So you use the word struct, then the name you want for the type, and then you give a list of the members and then put a semicolon at the end after the closing curly bracket. We'll see later that there is a related word, class, that defines something, in fact, extremely similar to this. But we're not ready to talk about that just yet. I just want to bring in the idea of structured data into the C++ course so we can work with more complicated things for a little while before we go any further. So here I'm defining a brand new type called point. And of course, defining a type doesn't actually create anything. It doesn't actually create any data, but it means if I want to, I can declare variables of this type, and then I can pass them around the program. And that's what I'm doing down here in main. So on line 19, I am creating a new variable called p, and on a diagram I would draw that like this. And this is very similar to what I would do in CSC 111, so reviewing some of the structure tracing or structure definition videos from that course might be helpful if it's been a long time. So on line 19, I make an object of type point called p, and each point object contains two, and we call these things members. The contents of the point object are the members of the structure, and they are called x and y. Notice that x comes first and then y in the definition that I've given. When I provide an initializer for a structured data type defined like this, and we'll see later there are lots of other very complicated ways of defining structured data types, when I define a structured data type with this simple notation, if I provide an initializer with curly brackets, then what I do is just go left to right in the initializer and I assign each member as I go. So in this case, I initialize the member x to be 6, I initialize the member y to be 10. So on a diagram, that would look like this. An alternative, if I would like to do so, is on line 21, I can provide an empty initializer. And if I provide an empty initializer, I'm still creating an object of type point. So there it is. And it's still got type point, and its name is going to be q. And q, just like p, has these two members, and they're going to be called x and y, and they're both going to be ints. But unlike with p, I didn't provide an explicit initializer. And so there are a few things that could happen here. What I've done in my definition of the type is I have provided a default initializer for each value. So in the definition of the type, when I put curly brackets, that doesn't guarantee that x will always be initialized to 0, because if I initialize my point object myself, it will initialize it as it did here to 6 and 10. On the other hand, we know already that the empty curly brackets are a way of indicating you want a variable, you would like it to be initialized to whatever sensible default value it should take on, and that's dependent on the type. We're, by using these empty brackets, leaving it up to the type to decide what its default value is. And for type point, I have provided those defaults for each member when I define the type. So in this case, on line number 21, the structure q gets the values 0 and 0. So it's initialized to whatever the defaults are for the member. members. But I could define whatever I wanted there. I could say this is -6 or something, and that means that if I use the empty initializer, then Q gets initialized to contain -6. Down here on line 25, in a minute I'm going to talk about this, but I'm proving the point that there are certain operators that are defined by default for structures. And then down on lines 28 through 31, I am demonstrating that we can pass values of structure types into functions. And one key thing to remember is the second law of assignment statements applies, which means that when I call a function and it takes an argument of type point, what I am passing in is going to be a copy. So a couple of other notes, besides the way that I define the type itself, the way I work with structured data types, at least at this basic level, is very similar to C code. So here on line 22, I am using the dot operator to access a specific member of my object Q. So the effect of line 22 would be to set the member called X to have the value 17. So the dot operator is a way of going into a structure, a value of a structure type, and asking for a specific member by name. And as we know from 111, I am only allowed to use the dot operator if the thing to the left of it, so in this case the variable Q, is actually of some structured data type. So that is to say, Q either is a structure or it's a variable of a reference type that refers to a structure, but not, for example, a pointer or something else. And so I can use the dot notation to initialize my structure if I'd rather not use these curly brackets. So I guess I'll update my diagram. And then down here on line 25, I'm making a third point object called R, and I'm setting that to be equal to Q. I guess I have to put that over here. So it's of type point. Its name is R. And it's initially, so I initialize it on line 25 with a default initializer, which means that the members X and Y of this object both get initialized to 0. But then on line number 26, I am assigning a copy of Q into R. And we know already that, of course, R and Q are two independent things, but I'm allowed to perform this assignment. So assignment is defined by default for structured data types. We'll see later in the course that we have the ability to supersede that. I could decide that I'm not allowed to copy certain things, but that'll come up later. So line 26 is saying copy everything from Q into R. So when we do this, if I copy one structure into another, I am doing a member for member copy. So I'm copying every member into the corresponding member in the result. And I guess I forgot to print out the value of R, so I'll rectify that. And then we'll try running this. And then I want to make one more point and move on to the next example. Okay, so P is 6 and then 10, and we can see I'm just printing it out with, so I'm just printing brackets and then the contents of each point. The idea being these are points in the plane, so I print them out with an ordered pair. And one, just to emphasize that the second law of assignment statements applies, suppose after I assign R to contain a copy of Q, I modify one of the members of Q. So of course, line 28, the assignment there has the effect of modifying the member called Y to be -999. And we can see, of course, that doesn't modify Q, or so it doesn't modify R, because R and Q are two separate things. I'm only modifying my structure Q. Even though I copied Q into R, that doesn't mean R and Q will always be equal to each other, just that as of line 26, one is made equal to the other. And so, of course, all of the usual laws of assignments apply here. We can copy one thing into another. That doesn't make them the same object. I can pass my structure objects into functions. When I do it like this, I am passing a copy. I am allowed to pass references, just like anything else. We'll see that in one of the next examples. And then I can define a structure type like this, where I can provide a sensible default value for each member. I suppose we never actually verified that that works. So let's see what happens if I initialize Q with a default constructor, but not assign new values to its members afterwards. And we can see here that I copy the value of Q into R, and that -6 that was assigned to Y by default propagates through. And then I guess I modify the member Y of Q to be -999. Okay, so I can define structured types just like in C, although I use different notation, and otherwise they behave pretty much as they would in C. We'll notice, however, that we're opening up Pandora's box here. There's a whole bunch of other features of structured data in C++. Again, one of the initial motivations for creating C++ was to allow more flexibility and control over how types like structured data types work. And we'll begin seeing that in a couple of weeks. We're just going to maybe see a couple of shadows of that today. So my next example is this one. which is what I have here, is a structure I'm defining for a shape, so a basic way of representing a rectangle. And I suppose a rectangle, I can represent rectangles in all sorts of different ways, but I suppose a simple way would be to say the rectangle has a width and a rectangle has a height. So if I store both of those two things together, then I guess I have enough information to describe a simple rectangle somewhere in space. So here I've used a structured data type to refer to that, and I've defined a simple function that computes and returns the area of a rectangle. Now we'll notice later in the course, for some reason I have an affinity for using rectangles as an example of structured data types. We're going to see them a lot later in the course. But for now, we're just going to verify that we can use these structured data types to store some sort of complicated, non-trivial thing. I mean, this is not that non-trivial, but I think it isn't trivial. So we'll try running that. And this is, I guess, demonstrating that I can construct these rectangles. I can assign them an initial width and height like this. I can then call this function getArea. I can pass in my rectangle, and I can compute r.width times r.height. One thing we should observe is, now this structure is not very complicated, but we often find, just like with vectors, that we don't want to pass copies around our program if we can avoid it. And one wonderful benefit of the reference syntax in C++ is that if I have some code that's taking a copy and I no longer want to take a copy, I want to take the original, but I want to lock it down so that nobody can modify it, it's really easy for me to just change rectangle r to rectangle constant reference. Unlike a pointer, which is what I'd have to use in C, I don't have to change the notation. Because this variable r is going to be another name for whatever gets passed in, so this variable r is the original thing, I can use the dot operator directly. There's no need to use something like the arrow operator as I would in C with pointers. We can see that that still works. Now we're going to come back to the rectangle structure in a couple of videos when we talk about something different, because we're going to use rectangle and some other shapes to prove a different point. But here is evidence that I could use a structure to store something other than just a point in space. Okay, but that's not that exciting because it's still sort of a strange, almost trivial geometry example. Let's take a look at this. So here is a structure type that I might use to store information about a student. So an example being their student ID and a list of the grades they've gotten in their courses. Now, I mean, if you're watching this video, I imagine you're in this course at UVic, but just to remind you, at UVic, final grades for courses have type int, and they are percentages between 0 and 100 inclusive. And so I could store all of the grades for all of the students' different courses in a vector of type int. And to keep track of all the records for a given student, I guess it makes sense. I want to bunch these together. So I want to have a student ID and a list of grades that can be of any length, because we have no idea how many courses a student has taken. And I want them to be stuck together inside of one object. And so we'll just try compiling this as it's written, and we'll see that, of course, much of it is incomplete. We have to start somewhere. Now, of course, this warning here is pretty nasty. When we get the no return statement warning, we better make sure that's because that we haven't actually written the function yet, because there should be no reason that warning should ever occur in practice. So I have some simple functions here, and then I want to comment a little bit on some issues that we have with this representation in terms of what control we, the programmers designing the type, have over how the type is used. And that's going to put a bookmark somewhere that we can come back to in a couple of weeks. So here I've got my type student, and it contains a student ID. And again, at UVic, a student ID might look something like this. So V, and then usually, 0, 0. I think we're about to get to 0, 1, 1, 2, 3, 4, 5, 6, or something like that. So I'm going to store that in a string because I don't know whether this V might change to some other letter later. I don't want to trust that it can always be referred to just by this numeric part. And then I'm going to store my list of grades. And a student can have 0 grades on file, or they could have 100. I have no way of knowing. That's why I'm using a vector for this. So down here in main, I create these student objects in a variety of different ways. So one of them is I create a student object with these empty curly brackets, and we'll notice again that when I do that, I get a sensible default value for each member. And in that case, it's an empty string and an empty list of grades, so a list of size 0. And then down here on line 41, I create a student object by initializing each member myself. So we initialize the members in order. So the initializer for the string, the student ID, is this. And then this thing here in the curly brackets, well, that's an initializer for a vector of ints. So it makes sense I provide that second. That would be my array of grades. Whereas up here, I assign to a.studentID, my student ID string, and then I assign, well, I guess you couldn't call this assignment. I use the pushback function on the grades vector. So a.grades is a vector of int, which means I can use pushback on it to push back all of the grades that I want to add to the array. And then I call print student. And we can see up here, print student prints out takes a student object by constant reference. So it takes the original, it doesn't take a copy, but it's not allowed to modify the original. And then it prints out the student ID, and then here is where we want to print out their grades. So I'm going to begin with that. Let's start by printing out all the grades corresponding to this student. So I might write something like this. I already have grades are, so I guess I just want to print out a list of the grades. So I'd say for auto grade in s.grades. S.grades would be my array of grades, so the name of the member is grades. And so I can just go inside of my structure S and I can ask for the member .grades, which is a vector of int, and then iterate over that. And I'll just print out each grade and then a space. And then when I'm done, I'll print out a new line. Now, we still haven't written this function compute GPA, and we don't need to do that just yet. We're not calling it anywhere, so I'm going to leave, we're still going to get this creepy looking warning, which shouldn't be too big of a deal as long as we don't call the function anywhere, and we're not doing that. We can see here, though, it does seem to be printing out the grades correctly. So the first student, student A, has 84 and 100. The second student has 90, 70, and 80. So that's enough, I guess, that we have some output being generated. We know the grades are being stored correctly. Now I think we can begin working on computing the GPA. I think what I'll do is I'll add a call to that down here. GPA is, and then I'll print out the result of calling compute GPA on the student S. So one thing to observe is, as I said earlier, at this university, grades are integers in the range 0 through 100 inclusive. So they could be 0, they could be 100. Some very lucky or unlucky people actually do indeed get those numbers, but they can't be anything else. And one interesting thing to observe is that we can create a type to refer to a student, but it's on the honor system that we respect any restrictions placed on what grades can be. Because an int can store anything. It can store -5, it can store -1 million, it can store +1 million. And although I'd prefer it that grades be valid, so between 0 and 100 inclusive, there is nothing I'm doing at the moment that prevents somebody from adding a weird invalid grade, like -10. And the same is actually true about this example with rectangles as well. And it's one of these things we're going to come back to a lot later. So I have a rectangle with a width and a height. And I can store those parameters, so there's the width and there's the height, just like earlier. I can store those parameters in this structure. And as I said, I mean, a rectangle is only barely non-trivial in this formulation, but it is actually a bit more complicated than that, because I guess I could argue that it doesn't make sense for a rectangle to have a negative width or a negative height. And yet, if I'm using type double, because I want to allow widths like 0.5, well, type double does allow negative values. I don't have the same workaround I might have by using an unsigned int or something. And yet, when I've defined my rectangle structure, I've just said that there's a width and a height. And with this almost trivial formulation, there is no way to prevent somebody from throwing in some weird negative width or negative height. And if the width is negative, what does that mean the area is? It makes no sense. And so the way I'm defining structures right now is too simple for what I might want to achieve later. Maybe later I want to force every rectangle in existence to be valid. I want to make it impossible to create a rectangle with a negative width or height. And so small steps, we'll handle that in a couple of weeks, but that is something that's on the horizon. Not just making up these types that are buckets of data, as we had in C, but also being able to control how the type gets used. And that's true of rectangles, and that's true of this student object, where the grades array is meant to be more than just a vector of ints. It has other restrictions that we want to actually enforce. But for now, we'll have to leave it on the honor system. So here I'm going to print out the GPA of the student, and then I'm going to go write my compute GPA function. So it says here that the GPA will be just the average of all of the grades inside the object. Now I know that, obviously GPA is usually computed with some bizarre, horrifying calculation that involves a number that is not between 0 and 100. I'm going to make an executive decision that in this course we're going to compute GPAs as just an average, literal average of all of the grades in the array. So I want to compute an average. I've decided the return type is float. I suppose I don't need 16 significant digits of precision for this. So what I'm going to do is just add up all the grades. So I'll start my sum at 0, and I'll just add up every grade in the grades array and then divide that by the total size. So I'll say for each grade in the grade array, so s.grades, I just want to add that into my sum. Now I'm taking care to make sure I'm computing an average here, and I'm computing the average of a bunch of integers. But of course the average could end up being a real value that isn't a whole number. So I'm taking care to make sure I don't accidentally compute a sum of ints, because that would end up, that would produce an incorrect average in some cases. So I make sure that by the time I do any division, I actually have a floating point value that I'm working with. So sum plus equals grade. And this is one place where some people that know certain tricks involving the standard library might observe that there is, I guess, a faster, for lack of a better term, I don't know, fewer lines of code way of adding up all the elements in a vector. But I'm a big fan of just coming up with any way of doing it. If using a for each loop is a good way of getting just about any task involving vectors done, so I like using that. And then I'm just going to return the sum divided by the total number of grades, which is going to be the size of that vector. So I get s.grades.size. And one thing we might want to think about here is, well, what happens if it's a brand new student? What happens if this student doesn't have any grades on file? But we'll just try not to think about that and instead look at these two examples where the student does have at least one grade. All right, so the average of 84 and 100 is indeed 92, and the average of 90, 70, and 80 is 80. So it does look as if compute GPA is working correctly. So we now have this ability in C++ to store these very basic structured data types, buckets of data, essentially, because that's all they are, is containers with each member being a piece of data, and any restrictions we want to impose, like that grades can't be negative, those are all on the honor system for the moment. And we're going to see later in the course there are ways of enforcing restrictions like that. But one thing we might want to think about for now, in fact, is this, which is independent of the whole structure question. We have to talk about structures at some point. Independent of that, what happens if I call compute GPA, but I hand over a student with no grades? What does compute GPA do? So compute GPA's job is to return a float, and I hand you a student, and I suppose it's valid that a student doesn't have any grades on file. What do you return? I mean, we don't want to divide by 0. We don't want to return, there can't reasonably be a GPA for a student that doesn't have any courses. So what do we do? And it turns out that's actually the main topic we're going to talk about this week, is what happens when a function is put in an impossible situation where it simply can't do its job. It's supposed to return something, but no return value makes sense in certain strange extreme cases.